Hello everybody. Today the semiconductor number 6, we talk about the first step of chip making. It's a chip design, and the chip design we have to make a chip. It's useful for the purpose of the chip, right? So some chip, the CPU for example, is used for scientific calculation. Then we need to provide all the necessary things for the scientific calculation. Or it's a financial application or website. Web server is more data transfer type. So I/O controller is more interrupt driven programming, and it's all different. So you cannot make actually you can make the very general purpose CPU chip like RISC-V and handle any kind of task, but it's like a general purpose. It's a compromise a lot of stuff. Okay, the industry tend to make CPU chip for specific purpose. So what is a specific purpose? What kind of hardware we have to design? What kind of logic we have to design? Then architect comes in. The architect think about what is necessary for this specific application, then design the architecture of the CPU chip, the semiconductor chip. And this chip, after architect is defined, then logic designer go in and design all the logic to perform best for the purpose. Okay, and after that, all the procedure to make it a chip is explained in the previous video, so you should watch the previous video. But the first things first, the architect. Here's a good example I use. Say we have $34 trillion debt in the federal. Okay, when they calculate, what do they use? Integer, right? Inside the computer they use integer to calculate the money. Okay, but $34 trillion is like 34 trillion divided by 2 to the x. This x is almost like a 32 bits. We need a 32-bit integer to express 34 trillion. The number is so large. So when you make a federal finance, the computer for federal accounting, 32-bit is not enough, because if you count down to the cents plus 2-bit, the 2-digit, that you definitely need a 64-bit computer. Okay, and before we didn't have a 64-bit integer. What did they do? The software did it. 32-bit, the 32-bit, use a 2 memory location. This is the upper 32 and the lower 32, and the software handle the large number like a $34 trillion. Okay, so there is always software solution, but why then you bother to make a hardware? Because performance. The hardware do it much quicker than software. Okay, so that's the purpose. So this is when you do the dollar amount, you have to use integer. The reason is you have to be very accurate in every digit, right? And what do you mean by not accurate? Okay, not accurate means the number of bits inside the computer is limited, and if you want to deal with much bigger number, it's impossible to be accurate for every number. So for example, you have 34.014 whatever. Okay, there is a limit you can express number of digits in the computer. Okay, that means you may have negative quite large number 4444 something, right? So the number of bits you have in a computer has to be spread into this kind of number, and that's the format we use, floating point format, floating point number. And what's floating point number is? Floating point number is like a real number, but the granularity means down to, human can think of any number in the real number. It's a number line, any number human can think of it. Computer pick only certain number, spread all over to certain range, and the range can be quite large if you spread more. So it makes sense, because if you are dealing with this kind of large number, then it's doesn't matter this value or this much. It's just difference is too small, right? So computer spread the number to cover more range, the higher range of the number to handle in a computation. Okay, that's called floating point number, and IEEE specify the certain floating point number. The floating point number, like this story, was done by software before, but now the floating number hardware coprocessor was created to make the calculation faster, right? And now floating point coprocessors numbers, it's combined into CPU, and nowadays the CPU floating point processors combined within. Okay, so even RISC-V, if the purpose is to control the IOs, you don't need this floating point number, because everything can be done by integer. So microcontroller type of CPU, we don't need this actually. So we can cut down this hardware amount, right? But once you go to the general purpose, you have to do computation, large number computation. You cannot do it with integer only. Then you have to have this. And RISC-V added floating point, the code, the instruction, like when you do add register A and B, there is a floating point add and register A and B, and floating point need multiple register location usually. So A represent the beginning of the several register, and the B represent the beginning of several register, kind of format you can use. Okay, so it does floating point format. We talk about floating point format a little bit later, more details. But that's what it is. It does A plus B, say real number addition. Okay, so and even integer, there is some details, like, okay, the two's complement, and one's complement, and the signed integer. It's all different. The signed integer is used top bit as a sign, and the remaining is largeness, like 0001 is 1, 0002 is 2, and whether it's positive or negative depends on this sign. But one's complement is you define positive number when top bit is 0, this is a positive number, and negative number is a complement of this. So as you see, if 0000, it's going to be 11111, right? 0001 complement is 11110. So there is a little inconsistency in this number system. So 2's complement is by adding 1 to 1's complement. This integer system is most popular. Okay, so when you make a ALU, which one you support? And most of the time, there are the ALU which can support. You can choose any kind of number system, but nowadays only use 2's complement addition, right? And that's most popular integer number system. Okay, and if necessary, the other number system use the software to do it. Okay, so the architect need to know your application use which one. If general purpose is usually 2's complement only, and the others just let them use the software to do it if the needs arise. Okay, so that's a way you make a decision about what will be in the hardware. The most often used performance critical one should be in the hardware, and other than that, it's you have always software solution. You can do it in software. Okay, so this kind of number system, this is integer number system already. There are multiple number system, but floating point has several others format too. Okay, so what the floating point? Let's look at the floating point. This is so-called 32-bit floating point. Okay, format. The top bit is a sign and has an 8-bit exponent, and mantissa is 23-bit. This is the detail part of the number, and this mantissa always has the implied 1. So this number is 1 point whatever the number, so it's going to be 1 point. This 1 is always added to the 2, 3, 7, 8, whatever. Okay, so this part is a mantissa, and the 1 is implied. We always have a 1, so we don't have to express it in the bit. We save that bit and use that bit for exponent. So exponent is basically this part. Okay, so you have an 8-bit. So the 8-bit is positive integer format. We talk about 2's complement first sign stuff. Okay, this sign is for mantissa, not for exponent. Exponent is itself is integer, but integer format is the positive integer, so it's from 0 to 255, and we need a negative number, so we bias down by 127. So if number exponent is 127, so 127 minus equals 0, that means exponent part is 0. So mantissa and exponent multiply exponent part. This is the exponent part, and this is the mantissa. Okay, So this is another example here. Now think about what is the smallest number you can express by this format. Okay, smallest number is like exponent is 0, so it's a 2 to the 1 27. This is the exponent, and the mantissa is implied 1 only, all 0. So this is the smallest number, right? And positive or negative decided by this sign. So in the real number, you have smallest number you can express by this, which is the positive side and negative side the same. This is a number. The largest number is what? The E can be, this can be 255. 255 minus 128. So 2 to the 255 minus 127, and the largest number is implied 1 and all the way 1. This 23-bit 1. This is the largest number you can express, and you have a plus minus sign bit. So the real number extend floating number up to this is the max, and beyond that you cannot express by this format. And when you do calculation in the computer, what's happened if number exceed is called exception flag. So there are several flag, overflow, underflow. You're familiar with it if you do assembly language programming. When you do add register A and B, sometimes it's overflow or underflow, and there are several exceptions. And the floating point processor also generate the exception flag, and it's going to be floating point overflow, floating point underflow, and there are several others. Okay, so when exception happen, then it's the software's job to about what to do, and the software decide, well, for our application this exception we don't care, just ignore it, or we have to modify and do different way to calculate this. Then we calculate it and get the result. It's up to software what to do. And exception happen occasionally, so it's not a performance issue. So when you design the hardware, you make sure generate all the exception and have the software's opportunity to take action for exception. Hardware wise, typically exception happen, then you don't have to do anything beyond that. It's wasting hardware because software handle it. Okay, so once exception happen, don't try to correct it by hardware. It's a lot of hardware and its performance degraded. Okay, so architect think about that kind of things. Typically 32-bit floating point format IEEE is defined, and most of computers follow this one. Okay, now it's questionable if like a RISC-V or any CPU has 64-bit floating point hardware calculation, because this is quite a lot of hardware, and if this is critical for the application, you should include in the hardware. Floating point ALU calculation is mantissa and exponent and shifter for exponent, shifter
you need a shifter because implied one location, and the result also has a shifter and a shifter, and combine them together into single floating point number. And this is quite a hardware for calculation. So 64-bit, not sure. Nowadays, for astronomy, they require even larger number. So it can be quadratic floating point, which is 128 bits. And I've never seen anybody make this hardware. It's done by software. The software calculate this is 64-bit, 128-bit floating point numbers. It's all done by software, and this is typically not included in most of the floating point package. But these days it's changed. The AI require even smaller 8-bit format, and there's no standard format. Every company using different format. Why 8-bit? Because when you say AI is like, okay, I make a decision, tomorrow if rain, go out. If not rain, I don't go out. What the probability of rain? It's 31.7658. This is totally unnecessary. So AI doesn't go for accuracy. AI go for a lot of number. The large matrix, you have a large matrix and input and multiply, and this one use next stage matrix. So a lot of matrix. This matrix size is like several thousand for the image AI. Okay, so a lot of calculation, but accuracy is not a question. So use 8-bit, so the calculation can be done very quick, because you have to do like the 100 million calculation for each decision making. Okay, so you rather make it small, simple, and quick to calculate. But this 8-bit format is, there's no standard. AI is an emerging industry, and every company uses different. The Google made a TPU, floating point. Actually, this kind of 16-bit, not floating point, 16-bit integer. 16-bit integer was used for graphics before, because you look at the screen resolution. Okay, well, 3000 is a very high resolution, right? And in order to express this position, you don't need a floating point. You need integer is good enough, right? So graphic CPU usually use integer to display 3D object here, and graphic is usually you have so many point. When you move, then like rotation and the parallel movement. Rotation is like a multiply matrix, right? The cos and the sine matrix, you have so many point. Like a graphics 3D model may have like the 2000 element. You rotate it, then you get the result. So that's the GPU, graphic processor. The graphic processor does this matrix calculation by hardware to speed up. Okay, so what is this? This is AI graphic processor, very similar, right? Yes, graphic processor happen to be very good hardware tool to do AI calculation. That's why everybody using a GPU for AI. But this is mostly graphic AI, okay? Because other type of AI is smaller matrix calculation, and this go several stage. But graphic AI use very large matrix size you calculate. So this is just GPU is just right to use for the AI. So it's not rotating 3D object or moving them around. The purpose is to calculate AI, and that's why GPU became so popular in AI. But that's only for one AI application, not every AI. As I said, some AI is the smaller matrix, and you have to calculate several stages. This is deep learning. Deep learning is like a multiple stage of calculation, matrix calculation. The typically graphic AI is like single 2 stages. So you now understand from architecture viewpoint, GPU and AI application right now is almost compatible. So GPU can be used for the AI calculation. So that's a story about the architect. It's for AI, accuracy is not important. It's the speed of many calculation. So you have a multiple CPU. You rack up like 128 CPU to do the calculation of matrix. The finished matrix calculation very quick, because the matrix is like pretty much everything can be done parallel, and you need an accumulator for matrix. The accumulator is a single ALU. You add them up, and that's become the result of matrix calculation. So speeding up the ALU and moving data around in the memories and the matrix calculator hardware, that's a AI hardware, it's almost identical to GPU. And so that's kind of architecture you have to think about to make a chip. And another one is called I/O control, like a robotics. I/O control MCU. This MCU is quite different. Okay, it doesn't do that many matrix calculation, no matrix calculation, no precision. Some of them need a precision for machine control. Precision is needed. So MCU may need floating point, but it needs more interrupt driven architecture. And you know how interrupt works is you have a register and ALU and the memory, and when interrupt happens, you're executing program, you jump to the interrupt program and use the same resources here. So before you use, when interrupt happen, you have to save the register content into this lower side of the memory. And in the software, you can do it by push or pop command. Those command for CPU is to save and load it back when the job is finished, kind of command. So this is a very long process. Each interrupt takes time in order to execute. Now this is the old architecture, and I haven't seen any progress in these areas, but I can tell I have some architect ideas. You can eliminate all of this. You can have very smooth interrupt driven CPU, MCU, and that means MCU act on any request from hardware immediately and execute the job right away. Okay, that's totally different from those matrix calculation GPU and stuff. This kind of MCU, the still in the industry is looking into this kind, but as far as I see, the progress is slower than AI. AI is conceptually much easier. For architect, making AI chip is not that difficult. The MCU is much harder. The MCU has all kind of, this old architect is like every CPU uses this method of interrupt, and this is kind of the standard way, and nobody bothered to improve this architect, but this can be definitely the new area to work on. Nowadays MCU is not that small chip. MCU handle pretty much everything you need outside of the server computer, okay, because the communication with the server is getting faster. The 5G and maybe 6G coming later, and for example, you manipulate the medical machine remotely, then the general purpose CPU may not be enough, because there are so many interrupt requests coming. You have to handle everything in timely, and that's a very difficult architectures. For me, it's more challenge than AI. Okay, so that's all for today. I hope you enjoyed it. Please subscribe if you like it, and click like button and leave some message. See, what do you think? If you are architect of the new semiconductor chip, what would you like to do? I like to read those comments. My videos comment is very small. Number of comment is very small because subject is very specialized technical subject. But I like to hear from you what you think. Okay.